So I think one of the most intimidating things that can happen to you when you're doing a public talk is to have your old professors show up. So what I'm going to do today is spend most of my time talking about which policies work and a little bit of time about how to get the right policies passed. I've been involved now directly and indirectly with over 200 policies that are now law, a lot of them overseas. But things like the renewable portfolio standards that have been adopted in 30 states across the United States. The first one was signed by Governor George W. Bush back in Texas. Pat Wood is his advisor. So many of you know those names. I'm going to start off, however, with a couple observations about climate science, which are designed to bring you to tears. Not actually, I hope so. But the point simply is that unless we move rapidly and at scale, speed and scale are the watchwords, there's no, there we go. There's little hope of a stable climate future. And in fact, we can push Earth systems into gross instability. I'm going to go through the climate science stuff pretty quickly because I think most people are steeped in it and want to get onto the policy. But there's just a few characteristics of it. So the first thing, this is actually a cool website. You can adjust to different sea levels and move the slider back and forth. So I got the slider right in the middle. Those little dots there, those are the trees on the Embarcadero. This is the kind of future we're looking at. The 1,200-year drought that the United States recently had. It's about the extremes. Scientists measure average differences. Humans experience extreme differences. The wildfires we had in California last year and the year before, some of the worst in California's history. Floods, this is in San Jose, right nearby this year, but there have been times when almost half of Bangladesh is underwater. Try to imagine that, a country of that many people, surrounded by people who don't love them. Just recently, we had this incredible cold snap when it was 40 degrees below zero in Chicago. This was the world on that day, and you can see this cold region up here, but look at the rest of the world. So what's happening is we have a protected climate from the real cold because of the polar vortex, which is this wind circulating and then the jet stream below them. That polar vortex is powered by the temperature difference between the Arctic and the temperate climes. As the temperature difference stops or melts because the Arctic's warming at twice the rate of the rest of the world, then the polar vortex weakens, and instead of being a tight circle containing that cold air, it becomes a wobbly disk. And so you get these downward wobbles, which is this cold spell, or you get these upward wobbles, which was this huge high-pressure system that plagued California for almost a year. So even if your averages are modestly different, the extremes are extremely different. There are now more than 40 million acres between New Mexico and up through Canada of dead pine trees. Why? Because there used to be really cold winters that killed all the pine beetles, and there's no more really cold winters. So if you want to see what climate change looks like, take a flight. Here's a really neat set of data from NASA about average temperatures in the US in the summer. So under normal distribution, you'd have a third cold, a third normal, and a third hot. Look what's happened with real world data since then. Is it going? Not yet. It's a movie, but it didn't work. I'll try it one more time. Oh well. It's a really great movie. It shows year-by-year changes from the 80s till now. Imagine this. But this is where we've landed, right? So your normal distribution, two things have happened. The average moved a little. Look what happened to the extremes. There's all this extreme heat that we never experienced before. There's a report called Risky Business that Hank Paulson, Mike Bloomberg, and Tom Steyer put out, which says that in a very large fraction of America, for 2 or 3 months out of the year, you get heat stroke if you're outside for more than 2 hours. And there's where those cold winters used to be, the stop the pine beetles. So the extreme becomes the norm. And this is the key theme here. What happens when you drive systems this way is you unleash natural systems that accelerate the whole damn thing. And some of these are starting to happen. And when they happen, they have no reverse gear. Climate change does not have a reverse gear. So the first one that scares me the most is defrosting the permafrost, the no longer permafrost. What are we going to call it now? There are massive amounts of methane and also soil carbon in the tundra. And when you defrost it, it can release. And if that happens at scale, it takes us into an Earth we just can't even imagine. And there is some evidence that it's starting to happen. Wildfires. This is a satellite view of the Camp Fire, the one in California that killed so many people. When a fire burns, biomass is no longer carbon neutral, right? Spitting carbon back into the atmosphere. Also creating a lot of black carbon, which is an absorption. And then Arctic sea ice minimums. Take a look at the difference in sea ice minimums between the 80s and now. So in not very much time at all, we have changed the face of the Arctic. And this is positive feedback in the scientific sense, a vicious spiral in the vernacular, because this white ice used to reflect the sun, and this dark ocean absorbs the sun. So the point is simply, first of all, that the extremes become the norm, and secondly, that as you push these systems too far, they dramatically exacerbate what we as human beings are doing to the atmosphere. So the next ones I want to do is a quick little bit of carbon math. Actually, Lynn Orr and I wrote an article 12 years ago called A Trillion Tons. 10 years, 8 years ago, something. Who knows anymore? So on the left is carbon emissions, and on the right is carbon concentrations. This is what we do to the atmosphere. This is what the atmosphere does back to us. So this is a business as usual world, unthinkable, but BAU. This is what happens if you don't have good policy. If we get really smart really fast, if we put a 90-degree kink in our emissions curve and we drive it down to 0 by 2050-ish, this is a 450 ppm curve, by the way, look what happens to concentrations. They don't go down. They're just flat at a 450 world because carbon dioxide stays in the atmosphere essentially forever. One of the weird characteristics of this, the perverse characteristics, is that under most reasonable scenarios, 650 ppm is harder than 450 ppm. Why? Well, take a look. If you can keep going up and then you drop down to stabilize at 650, you still have to get your emissions to 0. Emissions go to 0 for any stable concentration. Not exactly 0, but close to 0. But look how much farther you have to go down and how much steeper the slope is under most reasonable scenarios. The two things that are proportional to economic dislocation is this displacement on this curve. This is the amount of the industrial world we have to remake, and the rate of change. Are we retiring perfectly good industrial equipment or obsolete industrial equipment and simply replacing it? So what this argues for is that any reasonable future concentration requires an immediate U-turn in carbon emissions. There is simply no way around it, and the more you study carbon math, the less happy you will be. All right, this is my last bad news slide, and this is a really interesting slide, and it's a little bit complex, but I'm going to take a second with it. So for many millions of years, the Earth had a very stable oscillation between these so-called interglacial cycles and this nice warm Earth. And so essentially all the habitat that we're familiar with, all the animals we're familiar with, and certainly every human settlement has happened because of, well, lately we've been in this beautiful Holocene. It's a perfect ecological niche for human society. We have built our society around this ecological niche. The Earth system can become unstable. So basically what this chart is arguing is that as time goes by, you can maintain stability or you can lose stability. And if you lose stability, you go into what they're calling now hothouse Earth, which is all these systems going to run away. And we're at a point right now where with pretty heroic work, we can land again at a stabilized Earth, or BAU, it's a runaway. So the point is, we're not going to stop at 650 if we don't stop at 450. Partly because the economic challenge is too hard, and partly because natural systems go nuts. And nobody knows what this is like. We haven't been there for 65 million years. So the stability of the system is a key element here. All I'm trying to say to you now is speed and scale. We need to do the right things. And if you need speed and scale, you can't afford to do too many trivial things or too many wrong things or make too many errors in policy design. And that's the essence of the rest of this talk. So to decarbonize the energy system, you have to hit 4 sectors. You have to get the electric utility sector, cars, buildings, and industry. 80% of the carbon, roughly, comes from these 4 systems. So the first test of any policy is, will it affect one of these four systems? And if you cannot imagine how your policy will physically affect one of these four huge systems, you're not in the game. So I'm going to offer my first controversial remark, which is, tell me how divesting is going to change one of these four systems. Capital finds returns. That's what capital does. So if it's profitable to make crappy vehicles, there will be capital to make crappy vehicles. And if it doesn't come from party A, it'll come from party B. Starvation of capital doesn't affect physical, starvation of equity doesn't affect physical systems. Profit affects physical capital allocation, right? So I'm in favor of divesting because it's ethically the right thing to do, I think. But if you think that's a strategy for changing coal power plants into windmills, and it's never happened. Okay, what do we have to do? The first thing we have to do is extreme triage. Triage means focusing on the most important elements and chopping away the least important. That's kind of a heartless way of saying it. But let's start with what countries do we focus on. There are 185 countries signed the Paris Accords. 20 of those countries account for 75% of emissions. So if we win in these 20 countries, we win. If we lose in these 20 countries, we lose. So that's the first amount of triage. There's 165 countries. Of course they matter. But this is where the carbon is. Unavoidable. The second thing has to do with capital again. And this is really an important point. The world spends about $5 trillion per year on energy. And another $6 to $8 trillion per year on the infrastructure that sets energy patterns. So you're well over $10 trillion a year already going into our energy decisions. If that money lands on green choices, we'll be okay. If it lands on brown choices, we will not be okay. It's not a matter of conjuring up new money. It's not a matter of raising new taxes and inventing new programs. So I say this because one of the perennial debates in the UNFCCC climate negotiations is, how do we come up with $100 billion per year to help the poor countries? We should come up with that money. It's the ethical thing to do. But is it going to affect the energy system at scale? No. 11 trillion is the number we should be looking at. The consequence of that from a strategic perspective is that we have to focus on policy. Somewhere I had policy up here. Maybe I didn't. Next slide. Good policy, bad policy produces this kind of thing, and good policy produces that kind of thing. And it's really straightforward. Every time you write a check to your local utility, somebody is deciding where that money lands. Coal, natural gas, solar, wind, hydro, nuclear. So those are important questions that get answered through policy. And since we have so little time and so little political bandwidth, we better focus on the right policies. So that's what I'm going to talk about now. We have to choose the right policies, and we have to design them really well. And that's of course what this book is about. It's called Designing Climate Solutions. It's about how do you draft a building code that actually decarbonizes the building sector very rapidly. So the first thing we did is we're back to our carbon budget. This is business as usual globally. The colored boxes is stuff that has to go away. And those are the different sectors up there. Some are pan-sector, some are specific, like these orange ones that are industrial. By the way, the ratio of responsibility amongst these boxes can be adjusted depending on which policy you do first. So if you have a really strong fuel efficiency standard, you get a lot of credit for that. But if you have a really strong gas tax, that would give you credit. So these are fungible up to a point, but only up to a point. There is no magic bullet. You have to have policies custom designed for each major sector. And I'll explain why in a minute. One of the other things we produce now is what some of you will recognize as a McKenzie cost curve, except it's not a McKenzie cost curve. McKenzie created a curve like this that had your carbon abatement potential on the x-axis and your costs, either savings, negative, or expenditures on the y-axis. We built the same curve but with policy instead of technology for each rectangle. And it tells a very interesting story. One of them is you can do most of this stuff with a small number of policies for free. It requires political courage because the incumbents fight back, as we will see. There's new bills in in Wyoming just now being passed to subsidize coal. Socialism, Wyoming style. All right, let me start with the electricity grid. because that's the easiest to decarbonize. It's also the most important to decarbonize because there's this cute saying, which is kind of true, decarbonize the electricity and electrify everything. And you can electrify a lot of things. So we've all seen these cost curves. This shows the rise in production of solar PV and the drop in cost. It's an amazing story, right? Solar is now the cheapest source of new energy in the world in many parts of the world. And that happened in the last decade or so, not least because of Arun Majumdar and other people. Same thing with onshore wind. Incredible price drop. Here's a new one, offshore wind. This stuff is close to magic. The price has dropped by 50% in the last 4 years. The wind blows much more steadily offshore and at much higher rates offshore. If you put it more than 12 miles out, the Kennedys can't see it. It's important, right? They spent 12 years trying to permit that and failed. And now they're learning how to float them. So you can put them off the California coast. You couldn't put, the California coast drops, the floor drops very rapidly. But if you float these things, it doesn't matter if there's a floor down there or not, or how far down it is. So, and also these things are counter-correlated significantly to onshore wind, so you get a much smoother power curve if you put them together. So offshore wind is a game changer, I think. By the way, these things are huge. One of these windmills will power 8,000 homes, and they're as big as the Eiffel Tower. They're incredible to see. It's one of the reasons, another good reason for putting them offshore is you don't have to drive them around, which is really hard to do when they're that big. All right, let me shoot ahead here. Speaking of politics, and I'm going to get back to this in a minute. Your electricity bill decisions, your utilities are controlled by your state, not by the federal government. The federal government can affect it. But governors in the East Coast of America, where they have trouble siting windmills, have now targeted more than 18 gigawatts of wind. And at a 50% capacity factor, that's the equivalent of replacing 9 or 10 nuclear power plants. And that's just in the last few years. Cuomo just pledged 8 gigawatts a couple weeks ago in his Green New Deal. So those are really interesting numbers. Speaking of states, this is a map of the states that have clean energy standards. This is an outdated map. You can't keep up with this anymore. There were 7 governors elected with 0 carbon electricity pledges by 2050, or 2045, or 2040 even. That's pretty tough. None of these decisions went to Congress. They were decided by public utilities commissions, arguably the 3 most boring words you can string together. But that's where the action is. That's the people who get to decide whether you decarbonize the economy or not. Half of all the carbon in our economy goes through monopoly pipes and wires. And because they're a monopoly, there's a commission that controls them. And because there's a commission that controls them, there's a dandy policy target, right? And it's not focused on enough. The first objection everybody has when you talk about a zero carbon grid is the sun goes down, which it does, and the wind stops blowing, which also it does, and yet you still need electricity, right? So the instinctive answer for everybody is batteries. I just read an article that said if you put all the batteries in the world together, they could run the global grid for 8.4 seconds. It's kind of a stupid comparison. But the point is batteries are expensive. They're getting cheaper, but grid scale storage is so far a trivial contribution, and will be for some time. That's okay, and here's why it's okay. There are half a dozen other things you can do that are cheaper than grid storage. The first one is just use the existing system more intelligently. We have 134 balancing areas for electricity in America. That's about 133 too many. Because if you swap electricity easily across geographies, using existing power lines, it smooths things out radically. I have some charts on that, but I'm not going to bring them up. But just think for a minute. Seattle and San Diego never have the same peak demand and never have the same peak supply. They are hooked up with copper, but they live in different worlds. So let's bring them together, right? It's called comparative advantage. It's called, you know, the free market guys love this stuff. The second one is demand response. I studied power systems planning here at Stanford, and we were taught demand is whatever demand is. Just keep building power plants and turning them on. And so you always have about 15% more than you ever could possibly need. But why should demand be static? Why not manage demand in a way that's invisible to customers to help balance the grid? When I worked at the Hewlett Foundation, they put in these huge tanks of water in the basement. And they made ice in them. And so they bought cheap electricity at 2 in the morning when nobody needed it. And they did not run their air conditioners all afternoon because they just circulated coolant fluid through the ice. So what did that cost as a thermal battery? Steel tanks. A lot cheaper than fancy anodes and cathodes and electrolytes working together. So I sometimes say there's 125 million large-scale batteries in America already. They're called buildings. And they're thermal batteries. If you know it's going to be a hot day and a windless day in Texas, and these are things you know 24 hours in advance, pre-chill your buildings by a couple degrees. Keep it within the thermal comfort zone, but just, and then cycle your air conditioners half the time over the afternoon. If you look at managing demand, they've done some analysis across California. I think they found 6 gigawatts of dispatchable demand. That's a lot of energy. It's a lot of power, I should say, because my professors will call me out. So demand response, what does it cost? It requires a radio and a switch. And some software, of course. But those things are cheap compared to a new natural gas turbine. So demand response is a big deal. When they run open bids for demand response against dispatchable supply, the demand response came in at about a quarter the price. The next one is time of use markets. Charge more, charge less, depending on whether you have excess electricity or not. It's a straightforward idea. Flexible supply. If you run a natural gas turbine for a couple hundred hours a year in North Dakota, when it's really cold and the sun's not shining and the wind's not blowing, fine. The carbon footprint's negligible, 200 hours a year. If you run it 5,000 hours a year, now you're talking carbon. So we have all these gas plants. Let's use them for power, not for energy. Let's dispatch them for short amounts of time when we need them at a fraction of the cost of batteries. They're already out there. Grid infrastructure, building new transmission lines is close to magic. When the modelers model grid balancing in a high renewables intensive world, the more grid they put in, the easier it is. So they actually talk about the Earth as copper plate being the ideal. We're not going to go that far. And then finally, batteries. The point of all this is the utilities business model should be system optimization, taking advantage of every one of these possible attributes to balance out large-scale renewables. When you do it, and I'm not saying this, I'm going to quote Steve Berberick, who runs the California ISO, which is an incredibly complex machine, controls all the electricity in the state, keeps it up, keeps it alive. He says 50% without breaking a sweat, 60, 70% no problem. Somewhere around 80% he's got to think harder. So fine, we need some things for our kids to do. Let's take it to 80. All right. What are the policies that drive this? Really, there are 2. And this is part of triage 2. There are dozens and dozens of policies aimed at the electricity utility system. But the 2 are a clean energy standard or a renewable portfolio standard. You can argue for either. I actually like the clean energy standard. And creating economic value for grid flexibility one way or the other so that the grid operator, the utility, or the ISO becomes a system optimizer instead of somebody who just turns power plants on one at a time and back off. That's it. State Public Utilities Commissions is your target. I'm going to talk about them in a minute. Let me move quickly. How am I doing for time? I got about 8 more minutes. Does that work? 10 minutes? 10 minutes, okay. Vehicles are going through their own amazing cost reductions. This is the price of batteries plummeting. Look at these numbers, 35% one year, 23% the next year, 26%. The real lesson from this one is don't go into the battery business because you're going to get wiped out by smarter people. Except, Aaron, you can stay there. So this is all great, and it's going to keep going. It's pretty amazing, but it's not yet magic. We can't forget the internal combustion engine, and here's why. Here are 3 projections of the penetration of electric vehicles. There's the Energy Information Administration, which has a habit of having a really wavy curve up to today, and then they pull out a ruler. This is my group, this EPS, and this is Bloomberg. So if you can push up to 50, 60% sales, annual sales by 2035 or 2040 or so, that's a lot of electric cars. That's a major transition. But look at the fleet concentration. The gray is your internal combustion engines. The blue is your new electrics. And that's between now and 2050. So our back-of-the-envelope calculation argues that with your most aggressive electric vehicle program, we will still build between 2 and 3 billion internal combustion engines. So they better be good. internal combustion engines. And that's what this chart is all about. Fuel efficiency standards have been the single largest, I think, policy in America for abating carbon, historically. This started when Gerald Ford was president, and he doubled from 13 miles per gallon to 26 miles per gallon between 1975 and 1985. And then we kind of went to sleep for 25 years, and now we're doubling it again under the Obama regs that have been kind of suspended and kind of not. But this is another policy thing. This is a race to the top. This is the United States, China, European Union, South Korea, Japan, India, Mexico. All these countries are pushing into the 50 mile per gallon range. That's a really nice place to be for vehicles. And there's no reason why you can't get there relatively easy. There are a lot of options. I start with light weighting. The average car in America sold today weighs 4,000 pounds to carry around a 150-pound person or a 3-pound pizza, right? That's a really bad ratio. And they don't have very good thermodynamics ratio either. Improved aerodynamics. The bottom of an airplane, smooth. Look under your car, not so smooth, right? We've only looked at the top half of the car for aerodynamics. Something wrong with that. Low rolling resistance tires. This is where your energy is going. It's in heating up rubber and asphalt with crappy tires. Demassing. Oh, demassing with design too there's some interesting opportunities there. I drive a BMW i3. It's an electric vehicle, but what makes it a great electric vehicle is from here down it's aluminum, and from here up it's carbon fiber. So that car weighs 2,700 pounds instead of 4,000 pounds. It's pretty cool. Reduced auxiliary loads. There are now paints that reduce the interior temperature of a car by 10 degrees, and they look exactly the same as other paints. So air conditioning turns out to be a significant energy load, and the more efficient you make the car, the more significant that share becomes. And then, of course, transmissions and engines. We're not done by any means in improving these. This is a pretty rich menu. Car companies know they can do this. They'll fight about the timing and the intensity, but they can get there. So which policies drive radically better cars? A zero-emission vehicle mandate or incentive or combination, and fuel efficiency standards. So we're now up to, remember, 4 policies to decarbonize these 2 sectors. I'm going to turn to buildings quickly, and I'm going to go so fast that Gil Masters can't hear me, so he won't know what I did wrong. Where's Gil? Low-E windows, when I studied here at Stanford, these were a brand new technology being developed by Southwall over in East Palo Alto. They're basically clear insulation. And you can tune them so that for hot weather they keep you cooler, and for cold weather they keep you warmer. They now have 80% of the residential market in America, which is pretty neat. Lighting efficiency. The green bar on your left is lighting efficiency skyrocketing, lumens per watt. Look at the cost curve on the right. Like those things now cost under $1, down from like 20 bucks about 3 years ago. There's no reason to buy any other light except an LED light. And also they last forever, and they don't flicker, and you can tune in the color. Here's a nice example of policy at work. This is refrigerator efficiency. When I was in college, it was 2,000 kilowatt hours a year. That's about $400 a year by today's electricity prices. It's now 80% less than that, both in terms of dollars and energy use. Meantime, volume of refrigerators has grown, price has dropped, and reliability has increased. That's technology. But it's technology with a public policy element. California standards, Jerry Brown, Jerry Brown, Jerry Brown. These standards kept getting stronger and stronger, and the feds had to go along because no refrigerator manufacturer wants to sell Model 1 for California and Model 2 for the rest of the country. Optimizing heating and cooling. I just got a mini tutorial about the Stanford cogen plant. That's an extreme example of brilliance, but there's no reason you can't do it. So what are the policies for buildings? A great building code and great appliance standards. It's that simple. And when you do it, and by the way, this goes for every single policy, include continuous improvement. What do I mean by that? When Jerry Brown signed the original building code law, Title 24 in California, back when I was in college, he put in a provision that it gets tighter every 3 years. And there are technologists and economists in the California Energy Commission that decide how much tighter based on payback to consumers. So everybody wants their technology to pay back within, say, 7 years so that they can be written into the code as a performance standard. That means we used our narrow political bandwidth once, and we get a gift every 3 years of tighter and tighter building codes. So now California's buildings are 60 to 80% less energy per square foot corrected for temperature and size than they were before. Building codes is the only policy that's worked at scale in buildings, and appliance standards is the only policy that's worked at scale with appliances. They just work. Let's do them. And people object, well, it's not right for the free market. Let the free market figure this out. And I always ask them, what hotel did you stay in last night? Did you stay in a slightly cheaper one that didn't have smoke alarms and sprinklers? Or did you pay a little extra to make sure there was rebar in the cement? And the answer is, of course not. When you open your tap, do you have a cheap tap with slightly milky colored water? No, because these are public values, and therefore public standards are totally appropriate. So we accept public standards for fire safety and for food safety and for structural safety. Why not for climate safety? I'm not arguing against economic solutions, but I'm arguing against being blind to the solutions that work. All right, I'm motoring along. Finish quickly. Industry is the hardest because it's heterogeneous. There are some ubiquitous technologies. I'm going to skip a couple slides. Motors. Roughly half of all electricity is used in motors. Motors typically pump things or move things. The way most pumps work is they are turned on, and then a valve adjusts the liquid flow, which is analogous to putting a brick on your accelerator and controlling your speed with the brakes only, right? So why not control the electricity going into the motor instead? It takes a little more thought, a little more money at the outset, but some of these motors can save $500,000 over their lifetime per motor by moving that. That's a real number. There are opportunities to increase every kind of efficiency systemically. System efficiency is the biggest set of opportunities. It's also the hardest one to hit with a policy because of the heterogeneity of it and because you're moving lots of different things. But it's sticking with motors, simple, if you have skinny pipes with tight bends in them, it creates a lot more friction than if you have fat pipes with narrow bends. That's just a system design concept. If you're alert to the opportunities in efficiency, you're going to find those out. One that I love is what I've been calling substitute design for materials. So there are 3D printers for all kinds of things. I got to see 3D printers in China that are printing buildings. They print with cement. So if you print your stuff, if you're using additive manufacturing, then complexity is free. And when complexity is free, your design horizons expand dramatically. So this is finite element analysis of a bridge, right? And you only need material where the lines are. Most bridges are concrete slabs. Most of that material's doing nothing. It's just too expensive to build something like this. But that's going to change. I'm going to shoot ahead. Okay, so what works for manufacturing? This is one area where carbon pricing works really well. Because manufacturers are sophisticated, they're long-term, and energy costs are high. Efficiency standards for devices like motors are good. And then the new thing is carbon intensity for products. And what do I mean by that? Setting a tons of carbon per ton of cement or tons of carbon per ton of steel standard and making that steadily tighter. Buy California, a new law signed by Jerry Brown, does this for the state's purchase of cement and steel. It's pretty cool. You have to buy in the top quintile on a tons per ton basis. Okay, I'm going to wrap up. This is a map. This is a really important map. This is a map of carbon by country. That's China. That's the United States. And by sector. So transportation, industry, electricity, buildings, and ag. These big squares are where we have to focus our policy. I mentioned which policies matter. If we get those policies in those squares, you land at a decent climate future. If you fail with any of those squares or any of those policies, you don't. Again, it's math. There are substitute, you can have a stronger carbon price and less performance standards. There are ways to swap between these, but the essence doesn't go away. So in order to win those battles, this is the last bit I'm going to talk about. How do you win? You need what I call precision interventions. You need to understand who makes the decisions. It's the Public Utilities Commissioner. It's not the endowment manager, right? It's the person who drafts the building code. It's not the senator from Texas, for sure. Sorry. Neither of them. So if you do your homework, if you understand in detail what the decision-making venue is like, what's their statutory requirement? First of all, who makes the biggest decisions about carbon? Who can pass those policies I mentioned? What is their decision-making forum? What's their statutory freedom? What's their economic context? And then you mount a sophisticated, intense campaign to affect that decision. You can flip them one after the other after the other. And I know because we've been able to do it. Here's a little math. 50 states, 250 public utilities commissioners, roughly 5 per state, right? Those people control half the carbon in the economy. But 30 states don't matter. Only 30 states matter. 20 states are too little. Don't care about Vermont. So now you're down to 150 people. But I don't need a 5-0 vote. I'm happy with a 3-2 vote. So now I got 90 public utilities commissioners. And I know where they live, and I know what they do. And they have hearings. It's quasi-judicial. And you can intervene in those hearings. It's hard, it's sophisticated, but it matters. And that's the whole deal. Okay, my last slide. That's what you got to do. There are forums. I'll give you one more example, and then I'll be quiet. The building code process is a bunch of engineers under the auspices of ASHRAE decide on what a good building code, a model building code should be. And then it gets adopted as a model building code by a vote of towns and cities. Who knew? And then the DOE supports it, and then cities decide, cities and counties and states especially decide to adopt it or not. And then it becomes a code instead of a standard. That step where towns get to decide whether to adopt it or not used to be, yeah, sure. And now a few rapscallions got in the way. So there are 20,000 eligible voters. 500 of them voted last time, and they voted it down. So the building code is one of the most important things we can do. It's one of the most important policies there is. So what about those other? Who are those other 19,500 actors who failed to vote? A lot of them are in California. You know why? Because this is a code that California doesn't use. But we're eligible to vote. So let's get our act together. It's good for California if the rest of the world builds efficient buildings. They'll buy better windows and so forth. Anyway, it's just one example of don't presume that the answer is writing a letter to your senator. It might be. Do the homework. Look sector by sector, find the best policy, find out who makes that decision, and then, and only then, decide what your strategy is going to be. Let that drive your goal. Okay, I'm going to skip. I'm going to just go to the last slide. One more. There we go. So.
Well, folks, I told you that you're in for a treat, and I thank you for this wonderful sort of broad spectrum of things that you talked about, all the way from sort of utility commission policy to global. So let's open it up for questions, and as the tradition goes, we'll open it up to students first. So if there's students who want to ask a question, go ahead.
How does one go about, one like me, go about applying political pressure?
Applying political pressure? As soon as you have chosen a decision-making venue that matters, then a couple days study is an elixir to figure out what are the decisions coming before that body in the coming year or two. What are the groups that are organized to influence them? And then call them. Call up if it's I'll just give an example in California before the Public Utilities Commission. NRDC and a group called CERT are two of the most influential. You can call them up, they will answer the phone and say, I'd like to help, what can I do? And tell them what your skills are. And then they might say, I need a cost model for integrating solar with the grid, or I might need 50 people to come to the hearing, right? There's a bunch of different ways to do it. We did this precision interventions with air quality laws and energy laws all the time. And we would get, like when there was a pollution law coming up, we would get 100 mothers of asthmatic kids to come to that hearing. You win that venue. You win the vote, right? And that's what it should be. They're supposed to represent those asthmatic kids, right? They're not supposed to represent the owner of the coal-fired power plant. It's a public utilities commission. So that's what you do. You look at, any good argument has ethos, logos, and pathos, right? So bring in one of those. Do the analysis, bring in the kids, tell a story, whatever it takes. But make sure you're an actor with intensity at that moment. Choose a venue, choose the moment, act with intensity.
Students, you had your hand up.
I generally agree with everything that you said. I really, really appreciate the talk. One thing that I want to push back on, and maybe it's in your book, is you identify buildings and transportation as two major sectors for carbon emissions. But I didn't see a lot of discussion about moving us away from, especially here in the United States, a suburban, single occupancy vehicle mandate, et cetera. Why aren't we pushing for, and especially with the housing crisis that we have today, why aren't we pushing for denser housing, more public transit, and not just looking at, let's have everyone run an electric car?
I had to look at the table of contents before I answer. So we do have a chapter on urban mobility. The triage answer is you should do a hell of a lot of this in the fast-growing developing world, where the patterns are being set. In a country like America, where patterns are mostly set, you won't get as much result per dollar or per hour. We have another book called Emerald Cities, which we did for the Chinese Ministry of Housing and Urban Development, which is an urban planning guidebook, which they've now adopted most of. And the World Bank's going to translate it into a bunch of other languages and publish it themselves. There are fantastic opportunities. In the US, I think the new mobility options are quite interesting. I'm not a crazy advocate for autonomy, but I for sure am for electric vehicles. But what's really exciting is micro-mobility. You know, the electric bicycles and electric scooters and things like that. I bought an electric assist bicycle, and I commute 15 miles with hills each way. No problem with that thing. So anyway, there are lots of options opening up. Does that make sense?
Question over there, and then we'll come over here. Go ahead.
So with the large amount of importance you put on like building codes,
Yeah.
I know that would change all the future buildings being made, but with lots of buildings being a kind of grandfathered in, how would you incentivize people to retrofit their current homes or businesses to also fit those codes?
That's a really, really tough question to answer. There are some interesting programs in the Nordic countries. They're actually forcing retrofits. It turns out that the biggest cost of retrofit is customer acquisition and financing and paperwork, not the retrofit itself. So another idea is to do bulk retrofits where you basically tell a neighborhood, we're coming in, we will guarantee your utility bill goes down. You don't have to put a penny down. We're going to upfront the cost. We're going to share the savings with you. In order to do that, you need some pretty sophisticated and powerful actors. And here's who I think they should be. The utility. Utilities have 100% market penetration, 100% information on customer energy use. They have an army of blue-collar workers in every town and city in America. They're already under public supervision, and they can raise capital cheaper than anybody else. Not PG&E, but all the others. So let's have them do a little more. You can't replace, you can never recreate that many capabilities, but you may as well dispatch it for the efficiency side as well.
Student over here. Yeah.
Hi, I just wanted to build on the earlier question about urban mobility, which I noticed was sort of the biggest negative cost or sort of positive benefit policy in your cost solutions chart. And I'm curious, sort of specifically, what types of policies you included in urban mobility, because as you know, there's this whole range from massive public infrastructure, public transit, to sort of micro-mobility. I'm curious sort of what went into that metric. And I'm curious what your thoughts are on what we should be prioritizing versus cleaning up personal transportation versus pushing for more big public infrastructure, public transit investments.
Yeah. Quantitatively, there's a model called Urban Footprint developed by Peter Calthorpe and Associates. And there's some separate work that's been done in China, and then we've got some independent research. Basically, you can reduce transportation energy use by about half with good urban design, which is a big number, and in some instances more. Barcelona and Atlanta have the same population, and Barcelona has only 10% as much transportation energy use, and they have radically different footprint. So the menu, you have to put a rubber band around your city. You have to have an urban growth boundary. Portland, Oregon does. Really powerful policy. You want mixed use instead of single use, so people don't have to go as far. You want small blocks instead of big blocks. That's not something we're going to retrofit, but it radically changes transportation patterns, because with small blocks, you have permeability. You want small streets instead of grand boulevards. If you have small blocks and small streets, you have more throughput with less pavement. You do need good public transportation, but it doesn't have to be a subway. We can't afford subways. They cost over $1 billion a mile in America. This is mind-blowing to me. But bus rapid transit, the best BRT bus rapid transit designs in the world achieve subway speed, subway efficiency at 5% of the cost. There's one in Guangzhou that was built in 9 months that hauls 850,000 people a day. It's more than any subway line in America. It's a beautiful piece of, it's engineering as system design rather than engineering as hardware. It's really a beautiful piece of work. There are a bunch of them now around the world. There's more than 40 systems around the world. They're pretty incredible. I've ridden on a lot of them. You do need bike and pedestrian facility. The iron law of transportation is if you build it, they will come. So if you add lanes to a highway, you get more cars. If you add parking spaces, you get more cars. If you put in bike paths, people ride bikes. If they feel safe, and if there's things within reach, they will get on their bikes. If you add electricity to your bike, you expand the range from maybe 1.5 miles to maybe 5 miles. And so a little geometry will tell you you've really expanded your work and shopping and school and recreation and healthcare options when you make a circle that's 4 kilometers or 5 kilometers around. And then finally, car control. So we price streets at 0. That's the wrong number, right? And so they get overpopulated. It's economics 101. I'm going to give you some examples of car control because they're kind of amusing but kind of powerful. The obvious one is congestion pricing, which London and Singapore has. It costs £25 a day to drive what they call a Chelsea tractor, which is an SUV in London now. In Beijing, you have to win a lottery to buy a car now. And only electric vehicles is all they'll sell you. In Shanghai, you have to buy a permit to buy a car, and the permit costs $13,000 today. In Tokyo, you have to prove you have a parking place before you're allowed to buy a car. That would be pretty good. In San Francisco, they sneakily changed the meters pricing by a lot when it gets crowded. So they have congestion pricing. They just didn't tell anyone it's congestion pricing. It's called, they do it with parking instead of driving. I don't care. You can do a tunnel, bridge and tunnel fees as long as you get it done. The sneakiest one is Copenhagen. They measure how many cars are in the city in real time. It's a good song. When the city is 80% full of cars, they turn every light on all the main arterials coming into town red. And they leave them red for 1 minute and 45 seconds, and they turn them green for 15 seconds, and then they turn them red again. Works. It works. You can't put too many cars in a space without ruining the space. So let's just acknowledge that. It's a physical fact, it's an economic fact, and it's emphatically a social fact, and let's do something about it. And if you have to do it sneaky, that's fine. So.
Any other students? Yep.
From an earlier graph.
Can you speak a little louder?
All right, should I start? From an earlier graph, I saw that the composition of the economy of developed countries, manufacturing is quite high, and we see agriculture quite at the bottom.
Yes.
But when we look at developing countries, this is almost flipped.
Yep.
And so, from agricultural activities, we will see more of methane, for instance, rather than CO2.
Yep.
And so, in such a case, what kind of policies would work better?
Yep. Yeah. Ag and land use are hard. You know, my little chart there with 90 decision makers. So in ag, there are literally billions of decision makers, right? Whoever decides to buy a plot of land and farm a plot of land and so forth. If you do the quantitative triage, you quickly land on, obviously, stopping deforestation is the #1 thing to do. Dealing with cattle is probably #2, both how many there are, the land they're on, and what they're fed. There are some ways to feed them that drastically reduce the amount of methane they emit, both from their mouth and their other side. There are certain agricultural, rice with rice paddies is another huge source of methane. I think the way we ultimately have to handle that is by a mix of financial incentives and best practice centers. And I think back on the Green Revolution and also the extension agency services in America, where they transformed agriculture in both cases, actually around the world. mostly to the good with some significant errors. And we need that kind of effort to redefine best practice to offer both financial incentives and training to switch that. But I'm not going to pretend it's easy. That's why I focus on energy.
All right, let's open. You had a few more students. Okay, one more student, and then we'll open it up for yeah. Go ahead.
Hi, yeah, thanks so much for your talk. I'm just wondering about, you had kind of grid infrastructure as before energy storage on your slide, how to decarbonize the grid, and kind of this idea of the earth as a copper plate would be ideal. But I was just wondering if you could comment a little bit on how maybe transmission lines are maybe exacerbating wildfires and things like that, and maybe if even with those factors, transmission lines and grid infrastructure should still come before energy storage.
Yeah. So one has to differentiate between transmission and distribution. So transmission are the high voltage lines that sit on huge towers, and they typically go along interstate corridors and things like that. By the way, a very large part of the world should not have transmission lines, right? Because you don't want to destroy valuable ecological lands or important scenery and so forth. On the other hand, there are a lot of places where it's perfectly fine to put a transmission line. I mean, right down the middle of I-80 would be fine with me. So transmission helps you smooth. Distribution is what causes the fires, as a rule. The distribution lines are lower, they're ubiquitous, and they're in the trees. And you really got to trim those trees to keep them safe, and it's hard to keep up. I think the way to deal with the urban-rural interface is to accelerate the transition to decentralized energy, right? Let's just get rid of as many wires as we can. Let's do it now that we're rebuilding. Ultimately, there's going to have to be an insurance pool or something like that for burned down homes in the firelands. So you just need to take each piece of it. Distribution lines are obviously important in suburbia and in the cities. We're not going to do without those, but they're pretty safe there too.
Let's open it up to some other people behind. I think you had your hand up. Go ahead.
I'm curious, you didn't mention negative emission technology in your portfolio. I'm curious if you know the advocacy work of the Healthy Climate Alliance, Climate Restoration Alliance, the work in carbon dioxide removal, Arctic and albedo restoration, and land use restoration.
I don't know the organization. A snapshot on going negative with carbon is I don't think it meets the speed or scale requirements that we have. I think we should put money into R&D and with the hopes that it gets better. But just to do a quick bit of physics, to get about 10% of our reductions would require a system between 2 and 4 times as large as the global oil system with everything running backwards at a cost of today $100 a ton, right? To get around 10%. So at the point we're ready to muster up that kind of capital, trillions of dollars, let's hope we've exhausted all the other stuff first. Let's hope we've done the cheap stuff first.
But R&D speed and scale are the requirements.
Yes. Yeah.
Chris?
I wanted to go to one of your late slides where you had the boxes, and there was a large box associated with United States transportation. Do you remember that slide?
I think the one you're thinking of was actually carbon pricing. I don't know if I can find it quickly. Oh, here, do it the smart way.
China, India, and the United States.
Oh, this one. That one?
Yes, this one. So that blue box is transportation, and it seems one of the more recalcitrant ones from what you said about transitioning the fleet, the gray area. Where are the actors on that blue box? In other words, the U.S. transportation. Who do we need to go to?
That's a great question. So far in the U.S., there's 2 systems. There's the federal system and the California system. The Clean Air Act acknowledged the fact that California had pollution controls for vehicles before anyone else, before the Clean Air Act was written. So they grandfathered in a clause that says California can be as good as the feds or better, with certain conditions. And then any other state in the country can choose the California system or the federal system. This is both pollution and fuel efficiency laws, or carbon pollution laws. What happened is California shot ahead. California has a meritocratic air quality system. It's the best in the world. So the California Resources Board runs it. They have 1,100 people, of whom 800 or so are scientists. They have a bunch of air quality management districts. And they really are working to clean up the air, and they're very smart about it. So they developed, well before the feds, very aggressive fuel efficiency standards and carbon standards are the exact same thing. They're just called different things because one's at the fuel side and one's at the tailpipe side, but they're the same. 13 other states have now adopted those standards. They also require a mandate for minimum number of electric vehicles sold, and that mandate goes up every year. So those 13 other states plus California is now close to half the population of America. So you've got two countries. When Obama was in office, he harmonized them, and he harmonized up to the California standard. Trump's trying to turn it around, and the courts are going to decide whether he gets to or not. And this is going to be an interesting battle, and the attorneys general of all 13 states are lined up, and a bunch of nonprofit groups are working on this. The thing to do, the intervention point, is to make sure that, especially in those states that are new or kind of on the edge, like Virginia and Colorado, or ones that could come in like Pennsylvania, that they hear from people saying, we should have the cleanest possible air, we should have the best possible cars, why are we being left out of this? So to make sure that the governors who had the courage to adopt those standards get political rewards, and then to look for a few tipping point governors and bring them on board. When we get to more than half the country living under those standards, I mean, the auto companies don't want the rollback that Trump is proposing because they know they're kind of screwed if they have to distribute two different kinds of cars out there or different mixes of cars. So that's where it is. It's typically the air quality regulators, and those are an underappreciated and under-lobbied by the good guys set of bodies.
So Hal, let me ask you one question, and that has to do with this chart.
Yep.
But let's look at the third country of India, because there the infrastructure really has not yet been built. The buildings have not been built, and it has capital. The economy is growing at what, 8% a year.
Stunning.
And they're going to triple the electricity capacity within the next 15 years. That's the aspiration. So if you were to advise them to future-proof themselves, what would you suggest? What are the top 5 to 6 things you would suggest to them to think about? Just the framing of that.
I would have Arun Majumdar come back. No. I mean, the first thing I would say is strong standards make strong companies, right? And it's true. If you have things that don't break and don't burn up and don't pollute and don't hurt people, you have the potential to become a global power. And India has some global companies, but they're kind of located outside of India, like Land Rover, Jaguar, and so forth. So strong standards make strong companies because it puts the companies into a race to the top. And then I would amend it to say strong standards make strong countries. I love your word future-proof. So there's roughly 400 million Indians without access to conventional electricity. So clearly off-grid solar, and in fact I would look for an off-grid package of incredibly durable, rubberized, low cost, not just the batteries in the inverter, but plug in your cell phone charger, a cooked stove, whatever you can bundle together. I think the days of new coal in India are probably over. I don't think they're going to permit any more new coal plants, or they'll permit them, they won't build them because it's really hard. The Indian political system, as you know, is sclerotic and complicated. And so the more modular your choices are, the better, right? So solar and wind have a huge natural advantage. The Indian government needs to revitalize its utilities because the Indian utilities are broke and the Indian utility boards are ineffectual. So that's really important. I would say building codes would be the second most important. I would eliminate every two-stroke engine. They should be prohibited overnight, and ideally have a big electrification program, especially for, and then I would encourage micro-mobility. Like, there are 200 million electric bicycles in China now. That's a perfect vehicle for a crowded street in India. A car is not the perfect vehicle for a crowded street in India. So I guess in some ways it's just like this, only it's the advantage of a leapfrog, right? Which I think was coined by Amulya Reddy, I'm not sure, but he was one of the great Indian energy thinkers. And the idea is simply, you don't need to put in copper wire to use a cell phone. Skip it. So let's see how many things we can skip and how many things we can create these nucleation points and really accelerate.
Maybe you have one more question. And Sally.
So we talk a lot about an economy-wide price on carbon,
Yep.
regardless of the structure, and that was sort of noticeably absent. So I thought it would be really interesting
That's a great point.
to have your take on that.
That's a flaw in the slideshow. It's definitely included in all our models and our analysis. A price on carbon in conjunction with two other things: performance standards by each sector and a vigorous R&D. That's the magic triangle of good energy policy. You need all three. A price on carbon is quite effective in some sectors and not in others, and that's really important to understand. It's most effective in energy-intensive industry, and it can be a tipping point number in the utility sector if the utility sector is not being driven by other means. So there's the question of a slack constraint versus an actual constraint. So if you're under a clean energy standard that's very aggressive, the price on carbon in the electricity sector, you're just gonna things at the margins. Price on carbon does nothing for buildings because of the split incentive. People that design and build buildings never pay the bills. And very little for cars. And here's my thought experiment with cars. If you go to Europe, taxes on gasoline or petrol or diesel are about $4 a gallon. That translates to $400 a ton of carbon. So if we rename those taxes carbon taxes, that's all we got to do, then you can look at the impact of carbon taxes in Europe. And the point is it helps. They have more efficient cars, but they also have much better alternatives. And they still need fuel efficiency standards to get to where they need to go. So the tax on carbon creates an economic signal that's consonant with the performance standard, but not a substitute, even at $400 a ton, which nobody's talking about. California has the best carbon cap system in the world, and the design features are, it's in concert with these other policies. It has a price floor and a price ceiling. So whenever you hit the price floor, you issue fewer permits. Whenever you hit the ceiling, you issue more permits. And I think this is just a great idea. It rises every year. Well, the cap goes down every year. And then I think the price floor and ceiling rise every year. Larry will know. Is that right?
Floor goes up by about 5% a year.
So that's a real number. And maybe the coolest thing about it, or one of the great things, is it spits off about $3 billion a year, which all goes into low carbon technologies and deployment, and more than half of which goes into poor communities and communities most adversely affected by pollution. So I think it's a great idea. Unfortunately, most systems have been mal-designed. If you set a cap higher than actual emissions, but that's what they did in Europe for a decade, and with RGGI for a decade, and right now, I think the most exciting venues for this are China and Canada, and then I think Oregon might join California. So,
Well, Hal, as you can see, this conversation can go on for a very, very long time, but all good things have to come to an end. So let's thank Hal for this wonderful presentation.
thanks, Aaron. Very nice of you.